Hello everybody. In today's lecture we are going to talk about property testing algorithms that use random walks. And many of the concepts that we are going to look at today will relate to the notions of Markov chains, random walks, stationary distribution, and things of that nature that we have looked at in the past. Uh, Today's lecture outline will be the following. There will be two segments. In segment 1, we will be considering expander graphs and their properties, and then we will briefly talk about property testing algorithms to test whether a given graph is an expander or not. And in segment 2, we will be discussing property testing algorithms to test whether a graph is a bipartite graph or not under the promise of reasonably good expansion. So without further ado, let's get into segment 1. And for this, we will first need to understand what it means for a graph to be a good expander. And in general, expander graphs are graphs that are well connected. But nevertheless sparse. So there's a little bit of a tension between these two notions. If a graph is well connected, you expect the graph to have lots of edges. At the same time, we also are looking for sparse graphs. So this tension, as it turns out, can actually be resolved quite well. So we have what we call expander graphs that are really well connected, but are nevertheless very sparse. So these are very interesting combinatorial objects, but there's many interesting aspects to this notion of expander graphs. In particular, one of the aspects is that it's not just a combinatorial object, but it also can be viewed as an algebraic notion, could be viewed from probability theory, and so on. So it's a very interesting notion that bridges many diverse areas of study. So at this point, our understanding of well-connectedness is somewhat vague. So one could ask, try to understand this notion from the point of view of computer networks. And so what is this notion of well-connectedness? So what exactly how do we pin it down? How do we pin down the definition of well-connectedness? Okay, so let's look at a couple of examples. So here are two examples. One is a graph where there are two completely connected subgraphs joined together by some number of edges. Let's say some little o of n edges, or even O of n edges for that matter. And then there's this other graph that is basically a random graph. This is an Erdős-Renyi graph on n vertices, and each edge in this graph, each pair of vertices in this graph will have an edge between them with some probability c log n over n for some sufficiently large constant c. Now the question is, which one of them is well connected? As it turns out, the answer is that this Erdős-Renyi graph is the well connected graph, whereas the other graph with two complete subgraphs connected by some O of n or little o of n edges is not very well connected. And the reason for this is the following. If you look at the Erdős-Renyi graph, any which way we try to partition it into two large subgraphs, the number of edges connecting those two subgraphs is going to be big omega of n log n. Whereas if you look at this other graph with two complete subgraphs, the number of edges connecting those two subgraphs is only O of n, or even little o of n. So it's very easy to disconnect the graph on the left. You only have to remove the edges connecting those two complete subgraphs. It's harder to disconnect the graph on the right while breaking up the graph into two equal subgraphs. So this gives us a sense of what we are looking for in terms of what is a well-connected graph versus what is not a well-connected graph. Notice, for example, that the graph on the right, it's easy to isolate a few vertices because it's essentially a sparser graph. So by deleting a few edges, we can disconnect the graph. So that's really not what we're talking about. If you look at the graph on the left, removing a few edges will not disconnect the graph. So you really need to remove all the edges in the middle before you can disconnect the graph. So there's this subtlety here wherein even though it's easy to disconnect the graph on the right, it's still considered well connected because it's hard to disconnect the graphs so that the two subgraphs are large. So with that motivation, we're ready to formally define expander graphs. And as it turns out, this notion of expander graphs is captured by not just one parameter, but actually several different parameters. And intuitively, and they all end up being this capturing the same family of graphs, but each one of them comes with its own flavor. The first parameter is edge expansion. It's a well-known notion. It also goes by the name of Cheeger number or isoperimetric number. So given this graph G, the edge expansion is as follows. To compute HG, you consider all the possible subsets of the vertex set of cardinality at most half the total number of vertices. And for each one of these subsets, we compute this ratio, the number of edges with one end in S and the other end in V minus S. So here's a picture that we have over here. So if this is the set S and this is the set of vertices outside of S, this dou S, if you will, is the number of edges that are going from S to V minus S. And this ratio that we're interested in is dou S over the cardinality of S. And this quantity is minimized. We're considering the least such ratio over all subsets of the vertex set. Okay. And this parameter, this lowest ratio, is called the edge expansion. So if you intuitively think about it, the lowest ratio is obtained when you consider a way to partition the vertex set into S and V minus S so that the number of edges going out of S in proportion to the cardinality of S is the least. And every other way to perform this partition, this ratio is significantly is more. So that this captures the worst case cut, such that if you will, the strength of the cut is the poorest. In a similar fashion, we can also define the notion of vertex expansion. And this is very, very similar. It's also called the vertex isoperimetric number. It's just like in edge expansion, we're going to consider all the subsets of the vertex set of cardinality at most half the number of vertices. And here, we're going to consider the ratio of the size of the neighborhood of S over the cardinality of S. So here, this gamma of S is the set of vertices in V minus S with a neighbor in S. So going back to this picture, so if you consider the set S over here and V minus S over here, previously we counted the number of edges leaving S, but now we're not counting the number of edges, but rather the number of neighboring vertices of this set S. And And so the notion is quite similar. In fact, these two parameters, the edge expansion and vertex expansion, for graphs that are of bounded degree, are related to each other by a constant. And now we come to a completely different way of looking at expanded graphs, a completely different parameter called the spectral gap. So let's consider the graph G, and for simplicity we're going to assume that the graph is simple. It's a non-bipartite D-regular graph. And let's look at the normalized adjacency matrix M. So here the entries of M are either 0 if the edge ij does not exist, or the ijth entry is 1 over D if ij belongs to E. So 1 over D here can be thought of as a probability. So consider a random walk that is at vertex I. This 1 over D is the probability with which it would transition to vertex J. So this is called the normalized adjacency matrix, and it's also sometimes called the random walk matrix. So now let us consider the eigenvalues of this matrix M. This being a symmetric matrix, it's with rows adding up to 1. What we're going to have is eigenvalues ranging from 1 to -1. The highest eigenvalue is going to be 1 itself, and the remaining eigenvalues are going to fall between 1 and -1. And in fact, now, because this is a non-bipartite graph, the least eigenvalue is actually going to be strictly larger than -1. Now, the parameter, the spectral gap, is this gamma is given by 1 minus the maximum of either lambda 2, absolute value of lambda 2, or the absolute value of lambda n. When the spectral gap is large, as in at least a constant bounded away from 0, then this graph is typically has good expansion and is typically called an expander graph. Now, having an understanding of the spectral gap, let us try to gain an appreciation for how random walks behave in expanded graphs. As a quick exercise, consider a random walk on this graph, deregular non-bipartite graph. Convince yourself that this graph is going to have a stationary distribution. This random walk is going to have a stationary distribution of the form 1 by n, 1 by n, and so on. Essentially the uniform distribution. Okay. Now, having convinced yourself, and you may want to pause and convince yourself of this. Having convinced yourself of that, now consider a random walk starting at some arbitrary vertex x and g. Okay. We define px of t to be the distribution of the random walk after it has walked for t steps. Okay. And we define delta x of t to be the norm of the difference between px of t and the stationary distribution pi bar. Okay. And this norm typically will be the L2 norm, but other norms have also been used in this context. But let's stick with L2 norm. Now, delta of t is simply the max over all starting vertices x, delta x of t. Tau x of e, just to make sure we understand what we're talking about, this delta t denotes how close the distribution px of t is with respect to the stationary distribution after some t steps, regardless of where we started. That's where we are taking max over x. Now let's look at tau x of epsilon. This is the smallest number of steps needed such that you start at x and your delta x of t gets to within an epsilon, to less than epsilon, which means that the current distribution of the random walk minus the stationary distribution, when we take this the L2 norm of this difference, it's within this parameter epsilon. And this is with respect to a particular starting location, and when we want this to be agnostic to the starting location, we consider it to be this parameter tau of epsilon, which is the maximum over all possible starting locations, the worst difference possible over all starting locations x, tau x of epsilon. And this parameter is called the epsilon mixing time of the random walk. And here's an important theorem, that mixing time to get to within a 1 over polynomial in n difference with the stationary distribution is at most O of log n over gamma, where gamma is the spectral gap. So just to make sure we understand what we're talking about here, this tau of, remember, tau of epsilon is the smallest, is the time required to ensure that the distribution of the random walk is within an epsilon of the stationary distribution in terms of the L2 norm. Now, here in this case, we have specified that epsilon to be polynomially small, so we're able to get to a distribution that's very close to the stationary distribution within O of log n over lambda, or rather gamma. And this is the spectral gap. And notice that for expanders, this spectral gap is a constant bounded away from 0, which means that this right-hand side is simply just O of log n. So what that means is, for an expander graph, if you start a random walk at any location and allow that random walk to walk for O of log n time steps, the distribution of that random walk is going to be polynomially close to the stationary distribution. So this is a very powerful property of expander graphs. So now let's actually come to the problem of testing whether a graph G is an expander or not. So just to make sure we understand what we're talking about, the input is a graph G and you're allowed query access to this graph. And this is in the bounded degree model, so the queries are of the form, what is the ith neighbor of a given vertex V? So you can use these queries to perform random walks, because you can go from one vertex V to a neighboring vertex uniformly at random, and then so on and so forth. So it's perfect for random walks based algorithms. But even under this model, the two people who introduced this problem was Goldreich and Ron, and they showed that you need at least big omega of square root of n queries in order to be able to separate graphs that are good expanders versus graphs that are not so good expanders. And as it turns out, they proposed a very interesting, simple algorithm to test whether a graph is a good expander or not. The algorithm works as follows. You perform some theta of square root of n times polynomial in 1 over epsilon number of random walks. And each of these random walks is of length theta of log n. Remember, this theta of log n means that if the graph is a good expander, it's going to, these random walks are going to completely mix, which means that their distribution is going to be very close to the stationary distribution. And now After all of these random walks have walked this distance, you count the number of collisions. That's the number of times the same vertex appears as an endpoint for different random walks. Now, if the number of collisions is more than some threshold value, some CT, which is a well-defined threshold value, then you reject the graph. You say that the graph is not a good expander. Otherwise, you accept. So what is the intuition behind this? Now, if the graph is a good expander, these square root of n polynomial and 1 over epsilon number of random walks are going to completely mix. And if you recall the birthday paradox, well, these square root of n random walks are going to be such that there's not too many collisions if they are completely well mixed. However, if the graph is not an expander, there are going to be these random walks are not going to be able to mix well, which means the distribution of these random walks are going to be non-uniform, and there are going to be pockets of the graph where they're more likely to be found, and therefore more collisions are likely within these random walks, and they are likely to terminate in a lot more collisions. And so this is the key intuition behind this algorithm. So it's a very, very interesting algorithm, but Goldrake and Ron were not able to say much about this algorithm. They were able to say that the algorithm accepts good expanders, and this is fairly straightforward because these random walks, for good expanders, these random walks are going to be completely mixed, which means that their distribution is going to be very close to the uniform distribution, and this means that the number of random walks is chosen so that it's just shy of the threshold for significant collisions to take place. So you will not find too many collisions. Remember, for example, when we looked at the birthday paradox, when we set the parameter to 2 square root of n balls thrown into n bins uniformly at random, then we start to see collisions. But here, the threshold is such that the number of collisions will be the number of collisions will be small. Now, fast forward to 2007, Sumai and Solar presented an analysis of this algorithm. Of course, they had to choose suitable parameters in order to get the analysis to work. And what they showed is that the algorithm, the same algorithm as proposed by Goldrake and Ron, but with parameter adjustments, is able to accept alpha expanders. This is here we're using vertex expansion. Moreover, they also showed that this graph, this algorithm rejects graphs that are far, in particular epsilon far, from being alpha prime expanders. And here the alpha prime is at most O of alpha squared divided by d squared log n over epsilon. Now notice that this rejection happens only if the given graph is not only far from being an expander, it's actually far from being a worse expander than this alpha over here. So keep in mind that this alpha is going to be a parameter that is strictly less than 1. So and as a result, this alpha prime, when you square the alpha here, this alpha prime is going to be a worse expansion parameter. And so the rejection happens with constant probability only if the graph is both an epsilon far from being a worse expander. So the result is, in that sense, not very impressive, but even getting this result was quite a challenge. And then soon thereafter, there have been some improvements. but again, nevertheless, of the same general form. So the improvements were by Kale and Seshadri, and then Nakmias and Shapira, and they were able to show that the same algorithm can accept alpha expanders, and also with some constant probability reject graphs that are epsilon far from being alpha prime expanders, where here they've improved the alpha prime to be O of alpha squared divided by D squared. So they've gotten rid of this log n over epsilon in the denominator over here. But still, this alpha prime is now, it still remains as a function of alpha squared. So the open question is, can this alpha prime be reduced to, can be improved to alpha over some function of d, and not be dependent on the square of alpha. So this is the big open question. So this has actually been a very interesting question, mainly because the algorithm is so simple and elegant, but the analysis has turned out to be quite non-trivial. So we are the analysis is beyond the scope of our course, but the algorithm itself is something that we should be able to appreciate a lot. So with that, we come to the end of segment 1. In segment 2, we will be talking about testing bipartiteness.